Yeah, thank you so much for having me here in this beautiful place. I'm having a wonderful time and meeting lots of fun people. So it's been great so far. And also thank you for this opportunity to speak and to all of you for coming. I'm really excited to tell you about some work classifying modules of equivariant Eilenberg MacLane spectra. And I come to this motivated by ROG graded cohomology. And so I want to tell you a little bit about ROG graded cohomology. And to do that, I'm going to set the stage with some reminders from the classical non-equivariant setting. Okay, so in non-equivariant homotopy theory, maybe I like to think about nice spaces like CW complexes, where I attach cells, which are disks, along their boundary. And one of my favorite algebraic invariants is cellular cohomology. And I can take cellular cohomology with coefficients and an abelian group. And it has lots of nice properties. But let me just remind you that one in particular is that it has a suspension isomorphism. So I can take my CW complex and smash with, say, an n-dimensional sphere, and that's the m suspension of x. And then that just shifts the indices in cohomology. Okay. Maybe a really nice abelian group to choose is to work with coefficients in a field, say Fp. And then the cohomology of a point is just Fp in degree 0, 0 everywhere else. And that means that the cohomology of any space is a graded Fp module. Okay, so just a graded vector space. Okay, so now I want to move to the world of spectra and talk about the stable setting. So this cohomology, say with Fp coefficients, is represented by a stable object. So I call this an Eilenberg MacLane spectrum, HFP, and you can think of this as taking all of the Eilenberg MacLane spaces together. It's a particularly nice spectrum. We're working with coefficients in a field, and that tells us that we have a commutative ring spectrum. And it's defined by the property that its homotopy is just Fp concentrated in degree 0 to reflect our cohomological story. So I said the cohomology of any CW complex splits as a direct sum of shifts of Fp. Well, I said it was graded Fp vector space, so equivalent statement. And this splitting is reflected stably. So every HFP module splits as a wedge of suspensions of HFP. And if I want to write that really in symbols, I say, hand me any HFP module, Y, then Y splits up to weak equivalence as a wedge of suspensions of HFP. Okay, so this is a really nice property of this spectrum HFP. And in fact, more generally, Hopkins and Smith showed that whenever you have a commutative, or I don't even need commutative, whenever you have a ring spectrum whose homotopy is a graded field, meaning every non-zero homogeneous element is invertible, then well, take any module over that ring spectrum, and it's going to split as a wedge of suspension of the thing. Okay, so for example, HFP, its homotopy is just Fp in degree 0. That's going to give us a graded field. The case that Hopkins and Smith were interested in is a little bit more interesting. So you could look at Morava K theory, the nth Morava K theory. I'm not going to tell you what that is. Don't worry about it if you don't know. But the point is that its homotopy is a graded field. So it's Fp adjoin an invertible element, and you put that invertible element in some interesting degree. And this plays an interesting role in, say, chromatic homotopy theory, which is why they were looking at it. Okay, but in any case, anytime your homotopy is a graded field, then you'll get this kind of splitting for modules. So now I'm ready to turn to the equivariant story, and I want to tell you a little bit about ROG graded cohomology. So I'm going to let G be a finite group. There are some generalizations for compact Lie groups, but I'm not going to dwell on that here. In fact, for me, most of the time, this group is going to be just a cyclic group, CP of order P. Okay, so the spaces that we think about in the equivariant context are GCW complexes. These are formed by attaching orbit cells, G monosubgroup crafted along their boundary. If you prefer, you can basically think about a CW complex with a cellular G action. And Redon defined an integer-graded cohomology theory that takes into account the G action on these spaces and gives you a nice cohomology theory. And you notice pretty quickly that in this equivariant setting, you need coefficients, not just in an abelian group, you need an entire coefficient system. For example, even just on 0 cells here, I need to know the value of the cohomology on each orbit. And I need to know whenever I have a map between orbits that I get an induced map the other way on cohomology. So that's roughly the data of a coefficient system. Maybe more properly, a functor from the orbit category to abelian groups. Okay, but then when you're working in this equivariant context, there are really all sorts of flavors of spheres. So for example, if you take V to be a real G representation, you have some vector space with a G action, right? And you could 1-point compactify that vector space, and now you've got a sphere with some interesting induced action. We call this a representation sphere. And now because you have all these different flavors of spheres, you can talk about the V suspension of a CW complex. Pointed GCW complex. So what do I mean by that? The V suspension is just smashed with this representation sphere FV. Okay, and you might want a cohomology theory that takes into account that you have this nice V suspension that plays well with these representation spheres. And that's exactly what ROG graded cohomology is going to do for us. So what is ROG? Well, often people mean the real orthogonal ring of G representation. I'm just going to take it to be the free abelian group on the irreducible real G representation. I don't really need the ring structure here. And it turns out in this setting, you need coefficients in a Mackey functor. We've seen some things about Mackey functors already. And I'm not going to give you a precise definition here, but I think of a Mackey functor as a souped up coefficient system. So it's all the data of a coefficient system together with some wrong way or transfer maps. And then there's some compatibility between those. So Lewis, Peter May, and McClure showed that Redon's integer-graded cohomology theory extends to an ROG-graded theory if and only if your coefficient system extends to a Mackey functor. Okay, so this is where these Mackey functors come into my story. And what that means is that you take any alpha in ROG, some sum or difference of actual representations. So it's a virtual representation. You hand me some Mackey functor, some souped up coefficient system, then I can talk about the alpha cohomology, alpha equivariant cohomology with coefficients in this Mackey functor. Okay, and for me, one of the big advantages of this theory is that now I have a suspension isomorphism with respect to these representation spheres. So I could take my GCW complex and smash it with SV, and usually my suspension isomorphism shifts the indices, and indeed it does, and now it shifts by V, which was the representation, right? And so you see that I need to be able in this ROG graded world to add and subtract representations from the indices. And that's why we grade on a free abelian group of irreducible real G reps. Okay. So that was like a very quick crash course in ROG graded equivariant cohomology. Let me make things a little bit more concrete and talk about the C2 case. So C2 is a cyclic group of order 2. And let's kind of unpack a little bit what we get here. So first of all, there are 2 orbits. There's a point, C2 mod C2, and there's also C2 itself. So I have 2 flavors of cells to build my C2 CW complexes. There are also two irreducible real representations, the trivial and the sign representation. So really, there's a bi-graded family of representations. And the indexing here doesn't matter so much, except that those of us in the equivariant world have different conventions. So this is my way of telling the equivariant people my convention. But essentially, I'm following the motivic grading. The point is that I'm setting things up so this is a p-dimensional representation, and Q tells me about the number of sign representations. And the reason I do that is that then my representation spheres, which are the one-point compactification of one of these RPQs, have topological dimension P, and then Q tells me the twisted dimension. So I get this bi-graded family of spheres, and if you just ignore that second index, this is a P sphere with some C2 action, right? And then that second index tells me about the action. How flippy is this action? Okay, let me give you some examples. So here's some low-dimensional representation spheres. I've got a trivial circle, a reflection action on a circle, 3 different two-dimensional spheres. For example, if I take 2 copies of the sign representation, I'm reflecting in the x-coordinate and in the y-coordinate. So I'm rotating in the plane. I want to compactify and I get a rotating sphere. So that's S22 here, 2-dimensional sphere that's got 2 flippy dimensions, which turns into a rotation. Sorry, was that a hand? No, okay. Feel free to ask questions and just shout them out. We don't have to raise our hands. Okay, so we have these bi-graded families of this bi-graded family of spheres, all these interesting flavors of C2 spheres. And I want to talk about ROC2 graded cohomology. So I'm going to do coefficients in the analog of coefficients in a field. I'm going to take F2 coefficients. Well, I need a Mackey functor to do that. So I take the constant Mackey functor, which is essentially sprinkle F2 everywhere. Though there's a bit more detail to that, but I haven't told you properly what a Mackey functor is, so let me not go into the details now. Essentially, I want to work in an equivariant analog of F2 coefficients. And then this ROC2 graded cohomology of some C2 CW complex with F2 coefficients, well, because there are these 2 irreducibles, it's really just a bi-graded cohomology theory. So if you got lost with the super quick crash course in ROC graded cohomology, the point is I'm studying a bi-graded C2 equivariant cohomology theory in some analog of F2 coefficients. Okay, and I will sometimes drop the notation here, so I'll just write HPQ of X. And like the non-equivariant story, this is represented by a stable object. So it's represented by a genuine C2 equivariant Eilenberg MacLane spectrum. And I write essentially the same thing as the non-equivariant case, but with this little underline to remind myself that there's a Mackey functor lurking in the background. Okay, so we have this bi-graded cohomology theory, and what does it look like? Well, for example, we could take one of the simplest spaces I can imagine, a point with a trivial C2 action, and it turns out that this cohomology is quite complicated. So I've drawn a picture here of what we get, and when I draw these pictures, I'm drawing the topological dimension horizontally, and this weight or twisted dimension vertically, that number of sign dimensions. And you'll see that there's kind of a lot here. So let me try to explain this picture. But this is the bi-graded cohomology of a point as a C2 space with this analog of F2 coefficients. So what we have here is kind of these 2 cones, and every lattice point inside the cones represents a copy of F2. Then this upper cone, as a ring, it's polynomial in these elements tau and rho. So I have this whole polynomial ring, and it goes on forever. Similarly, the lower cone goes on forever. There's a little bit of a gap here, and then there's this top of the lower cone, I call that class theta, and theta is infinitely divisible by rho and tau. Okay, so when I write theta over tau here, I mean tau times that class is theta, and then tau times that is 0, since there's nothing there. Okay, so I haven't told you anything about how to do this computation, and in fact, I think it's due to unpublished work of Stong, though it kind of appears in a paper by Lewis. I'm happy to talk afterwards about how to do this computation, but for now, I just wanted to show you what we get. Okay, and so I call this ring M2, and it's a commutative ring, this bi-graded commutative ring. But because of this lower cone, it's non-Noetherian. So unlike the cohomology of a point in F2 coefficients, which is just a field, F2 in degree 0, which by the way is what we see here if we just restrict to the p-axis, like Verdon would. But if we look at the whole ROC2 graded picture, then the cohomology of a point is this infinite dimensional, really non-Noetherian ring. So when we talk about cohomology of C2 spaces, we're really going to have to deal with modules over a non-Noetherian ring, which I don't know about you, but it's not what I studied in my algebra course. So it's been interesting. Okay, this is a lot of data to carry around, so I tend to just draw a cartoon. They're double cones. We're meant to remember that there's infinitely much stuff in there, but roughly it's got this shape. Okay, and then it turns out from this computation, now we know the cohomology of any representation sphere because we built the suspension isomorphism into the theory, right? And so the cohomology of any representation sphere is just a shift of this double cone picture. So just kind of take this and move the generator from somewhere. Okay. I feel like I forgot to say something about this ring. And I don't know what it was. Maybe it was that theta times theta is 0, theta squared to 0. I don't know. Anyway, we'll see if we need it. Okay, so I now want to look at cohomologies of C2 spaces as modules over this ring. I always have this equivariant map from any space to a point, just press it. And so I'm going to get a module over this ring. And for example, if I take the cohomology of the other orbit, C2, then this is what I get. So again, this bi-graded picture with topological dimension horizontal and this twisted dimension vertically. And now it's a much simpler picture, just a bunch of copies of F2 concentrated on the Q axis. And these vertical lines are meant to tell me about the module structure. So, I take this class and multiply by tau, and I get this next class. And there's nothing sort of to the side, so there are no row multiplications here to show. But if I look at some other spaces, I'll have something else. So for example, there are spheres that are not representation spheres. And for example, I could take a free action on a sphere, give it the antipodal action. And when I do that, I get cohomology that looks kind of like this vertical strip. So again, all of these pictures go on forever, top and bottom. So I've got this infinite vertical strip. And again, a bunch of copies of F2. I've got all these tau multiplications. So this is tau local. And then I think I've drawn here the cohomology of S3 antipodal. So I can multiply by rho a few times, and then eventually rho multiplication is 0 on all of these classes. Okay, and again, I haven't told you how to do any of these computations. Would be happy to talk about it later, but I just want to give you kind of the flavor of what sort of things you get from this theory.
Could I ask you, just for the notation, in the left-hand column, for instance, you've got H2, C2. Does C2 mean the space consisting of 2 points interchanged by C2?
Yeah, so this C2 is 2 points swapping. I'm thinking of this as the orbit C2 mod E with C2 activity.
And with the SA to N, for instance, is that an N sphere with an action of C2?
Yes, so this SNA is meant to be the n-dimensional sphere with the antipodal action. That's what my A means. Yes, thank you. Okay, so again, it's a lot of dots to draw and I'm lazy, so I draw this cartoon. I'm just like, yeah, there's a vertical strip with all this stuff in it. Okay, so these are some modules over M2, the cohomology of a point that you might get as you're doing these computations. And it turns out there are lots of M2 modules. It's a non-Noetherian ring. It has a really complicated modular theory. But when you start doing computations, well, you run into all sorts of weird modules. And then amazingly, at the end of the computation, things turn out kind of nice. So here are some examples. And I claim these are nice. So this is pictures of the cohomology of the 6 different C2 actions on a torus. I computed these during my PhD with collaborator Eric Kogel. And I don't want to dwell too much on these computations, though that would be a fun talk as well. But the point I want to make today is really just the overall shapes that we see. So you'll see here, I've got 4 of these double cone shapes. They're all lined up along the p-axis. So that's like the cohomology of the torus right there on the p-axis, and then the double cones are along for the ride. That's because this is the torus with the trivial C2 action. Over here, I've got a similar 4-cone situation, but 2 of them have kind of shifted away from the p-axis. And we see, for example, that Verdon's cohomology on the p-axis would miss a lot of information for this torus. Okay, but again, the point is, I see a bunch of cones. Then here, these 2 look quite different. So these are cohomologies of 3 actions on a torus. And I see, say, the cohomology of S1 with the antipodal action, and then another shifted copy. Okay, and again, somehow these computations in this equivariant world in this ROG graded equivariant world are kind of notoriously hard. And these computations were complicated, but then somehow at the end, when we finally got the answer, it was always quite easy to tell our advisor what we got. We just had to tell him where are the double cones and where are the vertical strips, and that was it. So that was really the thing that I proved in my thesis, is that is what will always happen. If X is a finite C2 CW complex, then its bi-graded C2 equivariant cohomology in this analog of F2 coefficients is always going to split as a direct sum of these 2 types of things. M2, the cohomology of a point, the double cones, and these vertical strips, cohomology of antipodal spheres. And they could be varying widths, those strips, depending on what you get. So here's an M2 module that Eric and I named the spooky parallelogram. So it's like kind of Halloween-y, I don't know. Anyway, we were having lots of fun when we were doing these computations, but this is not the cohomology of a space. You might expect a diagonal strip where here everything is row local, but everything has tau torsion. That's not the cohomology of a C2 space. But you can have double cones, vertical strips, and they can appear together. Yeah, so a few things about this theorem. One is finite. I mean, finite in many cells. So I have a favorite counterexample that's finite type. And then it doesn't fall into this kind of structure. I should also say this is really surprising in the sense that you're doing these computations, you really do run into all sorts of weird M2 modules. There are these complicated extension problems, and then somehow magically at the end of the day, it seems like they all sew up to just be these 2 things, 2 flavors of things. Question?
What controls the width of the strip?
The dimension, well, in this notation, just the dimension of the antipodal sphere, but in general, the space, I don't know. So you could have many, right? I mean, for example, you could even take a wedge of a bunch of these of different dimensions, and then you get all sorts of different widths. Yeah. Okay, so yeah, so this is surprising, but it really does help with computations. Now you don't have to solve a lot of those extension problems. You can see that, well, there's only so many things it can sew up to, and you're done. Even with that said, in fact, it's still hard to do computations, even when you know it's only double cones. It's hard. Okay, so I was able to lift this to a spectrum level statement. So if you have a finite C2W spectrum, you could smash it with HF2 underline. The homotopy here is kind of like the homology of your C2CW spectrum, and that splits as a wedge of maybe representation suspensions of these two corresponding planes. So the Eilenberg MacLane spectrum and antipodal spheres smashed with it. And then we thought, well, maybe this classifies all HF2 underline modules. And it turns out you need one more piece. So with Dan Dugger and Hazel, we showed that any compact HF2 underline module splits as a wedge of representation suspensions of three types of things. So we need HF2 underline that's going to have these double cones. We need antipodal spheres smashed with it. That'll give us the vertical strips. And then what I call co-fibers of powers of tau. So tau is this element in M2, and that gives you the diagonal strips. And I really liked that that was like this nice symmetric story. Okay, so I want to tell you a little bit about the proof, because the proof of the structure theorem for cohomology that we just had double cones and vertical strips was really a game of mucking around in M2 modules and how they related to homotopy theory, for example, that M2 is self-injective and somehow really dealing with M2. But in this bigger classification, we took a completely different approach. So we used this theorem of Schwede and Shipley that says that there's a full equivalence between the category of HF2 underline modules and chain complexes of modules over this Mackey functor, constant F2. So if you're not familiar with full equivalences, the point for me is that that means they have the same homotopy categories. So the homotopy category on the left is the derived category on the right. Okay, so Dan and Christy and I, we described the compact objects here, the perfect complexes. These are, we did this by classifying finite dimensional F2 underline modules, and we found that there are 5 indecomposables, 2 are projective. And then we classified all the perfect complexes by doing like a hands-on change of basis algorithm. So a perfect complex is made of finitely many projectives. And we took some huge complex and we showed how to change the basis and split it into a direct sum of shifts of some basic pieces. Okay, so my point here is just that it was a very different approach. So the work in progress that I want to tell you about today is what happens at an on-prem. So there are some indecomposables you would write down immediately. There are a lot of things that are very similar here. The homotopy of HFP underline when P is an odd prime, and I think of it as a CP equivariant spectrum. Well, the homotopy also looks like some double cones, roughly. And there's some analogous sorts of things. Okay, you could take that spectrum, you could take the orbit and smash with it. You could take a free action on an odd dimensional sphere, and that'll give you these vertical strip sorts of things. And you could also take finite subcomplexes. It turns out that's not really enough in the odd prime. So I also have this EV, this egg beater, which is not a sphere, but it's like a one skeleton of a rotating sphere. And so for a long time, I was trying to write down all of these things. And I kept getting stuck proving this structure theorem for ROCP graded cohomology. And then I would find some more things. And then I'd be like, okay, back at proving the theorem. And I would get stuck. And I could never get unstuck. And it turns out it's because it's impossible. So with Jakob Grevstad, a PhD student at NTNU, and in work in progress, we have a draft, but still writing. We show that the classification of compact HFP underline modules is wild for P and odd prime. And if you're not so familiar with this representation theory perspective, morally, that means it's impossible to describe all the indecomposable modules. So if you had such a list, it would contain a list of every indecomposable module of every finite dimensional FP algebra. You might have seen this kind of thing show up when people talk about modular representation theory. So for example, the modular representation theory of cyclic groups is nice, but already if you take CP, the group ring FP adjoins CP cross CP, this is going to be wild unless the prime is 2. So I think I'm about out of time. I think I rambled too long at some stage, but I guess I just want to finish by saying how we approach this. And the idea is that we use a similar equivalence between HFP underline modules or the homotopy category and the derived category of modules over this Mackey functor, FP underline. And we use quiver representations to show that this is wild. Sorry, that's not quite true. We use, okay, maybe I can skip to that slide. Then I can tell you. Here we go. Okay, so we show that FP underline is representation finite. It has finitely many indecomposable modules. There are 2 projectives. Things looked great to start, and then it turns out it's derived wild. And because I care about the homotopy category of HF2 underline modules, well, that being derived wild, the perfect derived category is wild. That's what tells me this classification is wild. And it turns out in the C2 case, when we had that classification, it's because we were looking at a gentle algebra. Actually, the quiver that you need is the quiver we saw in the very last talk. The 1 and 2 with alpha and beta, mod alpha beta. So if I had known that amazing quiver would appear, I would have put it on this side. Anyway, thank you.
Thank you very much.
Can I ask you're doing things with mod P coefficients, but supposing you do them with p-adic integer coefficients instead, and then when you do your perfect complexes, you would have to probably have lattices and like the ZP lattices. And the possibilities for those complexes are more restricted, I think, for perfect complexes. Have you gone in that direction at all?
No, we should talk about that. I mean, I think, isn't FP a ZP module? And so aren't all of these perfect complexes already going to be?
Well,
In
no,
that,
because if you have perfect modules for this thing, then they would have to be perfect for ZP, and you couldn't just take any quotient of such a complex and have it perfect. So I think it's a different question.
Okay.
No, they should certainly.
Let's definitely talk more. I would be very excited about that. And along those lines, you know, I kind of have some hope that HZ underline for the C2 case is still something that we can classify, right? We can classify Z modules. We have the fundamental theorem for finitely generated modules over a PID. And so I guess I have hope that that situation is not so bad, and maybe Z2 is the way to approach that.
I just wanted to ask naively, if you have lens spaces, can equivariant topology be set up in a distinguished way that reflects?
That's a good question. And I don't know off the top of my head. So I have a feeling that in FP coefficients, it won't, but maybe in Z coefficients, or there's also a more generally Burnside ring, and you can start to work with Burnside ring coefficients, and it might there, but I don't know. Maybe someone else has a better intuition for that. Yeah, it'd be interesting to find out.
Something that you want about, so in the beginning when you wrote this RPQ, it felt a bit non-standard because usually I would expect to write how many times you get the trivial representation and how many times you get the sign representation, and you instead shows like P minus Q and Q. So why is this change of the
Yeah, this is really a point of disagreement in the equivariant cohomology theory community. I think many people would agree with you that we ought to grade in such a way that we just say how many copies of the trivial representation, how many copies of the sign representation, or of course, in more general groups, you know, each of the irreducible. But I think that I grade this way because my advisor was interested in motivic homotopy theory, and the grading in this sense matches. So there's a Betty realization functor. If you take a real variety and take complex points, then you get C2 space with the conjugation action. And so the grading matches the motivic grading. That's one argument. That's really why I do it. But I have justified to myself after the fact that I really like that then SPQ, a sphere, I can see that it's a P sphere, rather than if I wrote it in the other grading, it would be like a P plus Q dimensional sphere, and I'd have to keep doing that arithmetic to think about the dimension. But yeah, you could choose either.
Any more questions? If not, then let's make this.